Hello, I'm Sebastian. Welcome to Nine Trees podcast. Today, I will summarize and review the book. Quantum Theory by Max Planck is a foundational work connected to the birth of modern physics. Planck is widely recognized as the scientist who introduced the idea that energy exchange can occur in discrete units, a move that helped resolve puzzles in thermal radiation and opened a path beyond classical mechanics. In this book, readers encounter the early conceptual landscape of quantum ideas as they were being shaped into a coherent theory. Rather than presenting quantum mechanics as a finished toolkit, Planck focuses on the physical problems that forced a rethink of long-held assumptions about continuity, determinism, and the nature of matter and light. The result is both historical and technical in spirit. It explains why quantization was proposed, what it aimed to explain, and how it began to reorganize the relationship between theory and experiment. For anyone curious about how quantum theory began, this is a direct line to the mindset of its originator. I will give you key takeaways from this book. Firstly, the crisis of classical physics and the need for a new principle. A central topic is the way late 19th century physics ran into contradictions that classical ideas could not smoothly resolve. Planck presents the scientific setting in which mechanics and electrodynamics seemed powerful yet incomplete, especially when confronted with precise laboratory data. Thermal phenomena, radiation, and statistical behavior created pressure points where continuity assumptions produced implausible outcomes. In this context, the book highlights how progress often comes not from adding complexity to an existing framework, but from introducing a new constraint that reshapes what counts as an allowable physical process. Planck emphasizes careful reasoning from empirical regularities, showing that theoretical elegance must ultimately answer measurement. This theme also clarifies why quantum theory did not start as a philosophical preference for discreteness, but as a response to stubborn quantitative mismatches. Readers gain an appreciation for scientific method, isolate a well-defined phenomenon, compare competing models, and accept that a small departure from tradition can unlock a much larger structure. The broader lesson is that quantum theory emerged as a disciplined solution to specific failures of classical prediction, not as an abstract revolution invented in isolation. Secondly, blackbody radiation as the key problem. The book foregrounds blackbody radiation as the decisive arena where classical approaches struggled and where Planck's breakthrough took shape. The blackbody problem is attractive because it is both conceptually clean and experimentally rich. A cavity in thermal equilibrium emits radiation with a spectrum that depends primarily on temperature. Planck explains why existing formulas captured parts of the spectrum but failed to reproduce the entire curve across frequencies. This mismatch made the problem more than a niche detail. It threatened confidence in the ability of classical theory to connect matter, heat, and electromagnetic radiation. By tracing the logic of modeling the cavity and its interacting oscillators, Planck builds a narrative of constraint and necessity. The discussion shows how one carefully chosen assumption can transform a calculation from approximate fit to robust law. Even for readers who are not doing the full mathematics, the conceptual arc is clear. Equilibrium radiation is a stringent test of theory because it links microscopic behavior to a macroscopic measurable distribution. Understanding why blackbody radiation mattered helps readers see quantum theory as an answer to a concrete, highly structured experimental fact. Thirdly, energy quanta and the introduction of a fundamental constant. Another major topic is the introduction of energy elements, the idea that energy exchange occurs in discrete packets proportional to frequency. Planck's proposal effectively limits how oscillators can emit or absorb radiation, and that limitation yields the spectral distribution that aligns with observation. The book treats this step as a physical hypothesis with measurable consequences, not a metaphor. Closely tied to this is the emergence of a new constant of nature, now known as Planck's constant, which sets the scale of quantization. Planck's constant does more than adjust units. It marks a boundary between regimes where classical continuity works well and regimes where discreteness cannot be ignored. The topic also connects quantization with temperature and probability, underscoring that quantum ideas entered physics through thermodynamic reasoning as much as through optics. Readers see how quantization provides a lever that links microscopic constraints to macroscopic regularities. The larger intellectual value is that a single constant can reorganize an entire worldview. It forces scientists to reconsider what is measurable, what is continuous, and how physical systems exchange energy at the smallest scales. Fourthly, statistical reasoning and the bridge between micro and macro. Planck's treatment highlights statistical thinking as the bridge that makes quantum ideas operational. Thermal radiation is not just about individual events, but about distributions, averages, and equilibrium behavior. This topic explores how counting possibilities and assigning probabilities can produce precise physical laws, while also revealing the assumptions hidden inside classical arguments. Planck's approach shows that when you change the allowed microstates by imposing quantized energy levels, the resulting statistical outcome changes in a way that matches experiment. In other words, the quantum move is not only about discreteness, but about how discreteness reshapes the bookkeeping of nature. Readers learn why thermodynamics and statistical mechanics are natural companions to quantum theory, especially in early formulations where the goal was to explain observed spectra and heat-related behavior. This section also clarifies a subtle point. Quantum theory did not originally arrive as a full mechanical model of electrons and atoms, but as a rule that constrained energy exchange and thereby altered statistical predictions. The benefit to the reader is a clearer grasp of how microscopic rules generate macroscopic laws, and why probability became central to 20th century physics. Lastly, implications for physics and the road toward modern quantum mechanics. The final important topic is how Planck frames the implications of his proposal and how it points toward later developments. The book situates quantization as a starting point that influences thinking about light, matter, and the limits of classical description. Readers can see the early contours of ideas that later became central: discrete energy changes, frequency-dependent behavior, and the need for new conceptual tools when dealing with atomic-scale processes. Planck's work also illustrates how a theory can be initially modest in ambition, yet transformative in effect. Even when the early quantum approach is presented primarily as a successful rule for radiation, it naturally invites questions about atoms, spectra, and the structure of matter. This topic is valuable because it helps readers separate what Planck established from what later physicists built on top of it. The result is a more accurate understanding of scientific progress. Breakthroughs often arrive in stages, with one insight creating a platform for many others. For learners, this provides a roadmap of how quantum theory evolved from a targeted solution into a broad framework that redefined physics. In conclusion, this book is best suited for readers who want to understand where quantum theory came from rather than jumping straight into modern formalism. Physics students, engineers with curiosity about fundamentals, historians of science, and serious self-learners will benefit most, especially those who appreciate explanations grounded in real experimental problems. The practical benefit is conceptual clarity. By seeing the motivation behind quantization, readers strengthen their ability to reason from evidence, recognize when a model's assumptions break down, and understand why Planck's constant is not just a number, but a boundary marker for physical behavior. Compared to many contemporary introductions that begin with wave functions and operators, Planck's perspective is worth buying because it preserves the original logic of discovery, the link between thermal equilibrium, radiation spectra, and statistical reasoning. That origin story can make later quantum mechanics feel less mysterious and more inevitable. It also provides historical discipline, helping readers avoid common misconceptions about what was known when and why the first quantum hypothesis was taken seriously. For anyone building a long-term understanding of physics, this is a valuable foundational purchase. If you would like to support Max Planck, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.